This is the Nova 200 dual beam system. It is both a scanning electron microscope and a focused ion beam system. Today we're going to talk about how to actually use the SEM side of things. If you are just doing SEM, you do not have to do this particular step, but if you are going to use the ion beam, this one is quite important, and that is here under System to push the Wake Up button. What this does is it warms up the gallium source for the ion beam so that when you are ready to actually, you've had your sample put in and you're pumped back down, it's all ready for you to go. So as soon as you've done the wake up, you're going to hit vent. It'll ask you to confirm that you wish to do that. You say yes. You'll hear it make a few noises. You'll hear a hissing sound as it starts the venting process. And you're going to want to come over to the regulator here, over to the UHP nitrogen cylinder, and you are just going to open up the tank. Never ever touch the regulator. To know when you're actually at room pressure, you're either A, going to have to tug on the door, or B, you can actually listen for the gas escaping from the chamber from the nitrogen cylinder. The software is either a quadrant system, or you can go full screen with a particular data set. The way to do that is on the keyboard, just press F5. And then to go back to quadrant, just press S5 again. So even though you have 4 quadrants, there are actually only 3 data types that you're going to be working with. One is your electron beam, and that is represented in the software by this little electron model here. You can see it here and down in the lower corner of this quadrant here. The second data type is the ion beam imaging, which is designated by a little nuclei model. And then you have the optical view, which is shown by the light bulb. So these are the 3 data types. You can change which quadrant shows which data type simply with the 3 icons that are first along the task line here. So for instance, if I want this quadrant down here to be an optical view, I can click the light bulb and nothing seems to happen. And the reason for that are these green icons in the upper left-hand side. These represent the pause button. Okay, basically means you're not actively collecting information. And you can easily get rid of that and start the real-time imaging by clicking the pause. And so now this is live scan. In theory, you should be able to do any data type in any quadrant. One thing to recognize is the fact that the software on this is running on a Windows 2000 platform. It does impose certain limitations on the capabilities of the system. We have noticed that if you don't leave these 2 quadrants as electron beam and ion beam, that the probability that the software will malfunction is much higher. The chamber is vented. I am now going to put a sample in. Anything that's going to go into the vacuum chamber should not be handled with bare hands. Doesn't matter how clean you are. The simple fact of the matter is that your skin has oils, skin cells, etc., which get into the system and create contamination for samples. So as much as possible, gloves. So you're going to open it up. And one of the things to be very careful with this system is you do not want to allow the door to slam open. The manufacturer has arranged so that there's 2 glides that the system opens and shuts on. Unfortunately, only one of those glides actually has a stop on it. Here I have my sample. It is a standard pin stub that you can find in almost any catalog. And the stage area here has a hole on top. You're simply going to slide the pin into the hole, tighten down the set screw that's on the side, finger tight. It's a small screw, small fine threads. If you put too much pressure on it, you'll strip it. So just basically just finger tight. Check to make sure that it is solid, that it's not wiggly or wobbly. If you find that the top is good but the entire assembly is loose, very simple to fix. Here you can kind of see it's wiggling right now. Is hold the base and simply turn the cone section until it is tight. And then your sample is nice and solid. And especially if you're going to do high resolution work, having your sample be stable is incredibly important. So the last thing you're going to want to do before you close this door, every single time, is you are going to check the height of your sample. So here we have a height measure. Basically what you're going to do is you're going to simply set this down on the stage, and as long as your sample is beneath this projection here, you're good to go. Now, sometimes if you're coming in here, you may have a particularly large sample. Let's say that you're doing a graphite puck. Those often are close to 1 inch tall. Those will not fit on the standard stage holder here and still fit underneath the height measure. For that purpose, we actually have a special half height section that can be put in and will get you about another 10 millimeters of height that you can use. One of the reasons why this is so important is inside here there is a cone-shaped piece. The pole piece, it's the final part of the electron optics. The end of it is very, very thin metal. So that is why it's so important that you check the height every single time. I know that we're good. I'm going to slide the door closed. Apply a little bit of pressure at the bottom of the bar on the bottom, so to make sure you've got good seal. And now we are going to hit pump. And you'll hear the system make some noise in the background. As soon as you hear the pitch change and or see the OmniProbe system here start to move, you're good to go. You can let go. What we're going to be looking at is down here in the software. We have an icon that represents the vacuum state for the microscope. If you'll look now, you'll see that right now we've got 2 green sections and an orange section. If you hover the mouse over that icon, it will actually give you a breakdown of the pressures inside the system. Whenever you come in here, these 2 pieces that are green, they represent the ion column, and the E-beam column should always be green. If for any reason you come in and you find that they are not, find staff immediately and inform them. The other section is orange because right now it has no idea what the vacuum state is. This uses a magnetron gauge, which is only good down to about 10 to the negative 4. Anything higher than that, and it can't register anything. Just like the venting process, it'll take 2 to 4 minutes. You'll know when you're getting close because you'll hear a thunk as it switches between the turbo pump and the mechanical pump. Usually after that, it only takes about 20 seconds before the system is actually at vacuum. Along here, you have a series of icons. These are going to be some of the primary ones you're going to be dealing with. Almost everything that I'm going to talk about as far as icons can also be found in menus underneath the tabs along the top. Over here on the side, these are also pull-down menus. First one is beam control. The second one is navigation. This gives you control of your stage. Third one is for patterning, primarily for the ion beam. This one is for measurement and annotations. This one here is for doing different detectors. This one here is a combination of pattern and stage. Our last one here is the alignments, which you as a general user should not be touching. Going back to the beam controls, waiting for vacuum to improve so we can get started. There's that thunk sound I was talking about. So this should turn green momentarily, like it just did. And when it does that, here where it says column, it was grayed out. It now actually is not, and I can click beam on. It will turn yellow, showing that the beam is actually on. Just like with the optical view earlier, we're not seeing any actual image, and that's because the system is paused. The nice thing about the pause is the beam in question is being redirected into an acceptor cup, so it's not actually interacting with your sample. We're going to unpause it, and we have an image. First thing, I want to zoom out. To change magnifications, the easiest way is the MUI, Manual User Interface. And the center biggest knob is magnification, and I can just simply rotate the knob and zoom out. Another way of doing it, use the keyboard plus or minus. That will double or halve your magnification level. Another way of doing it, up here along that icon bar, there is a section called magnification. You click on that and it lists the 9 most common magnifications. Last, under beam controls, there's a magnification section and there's a slider. You can either use the arrows or drag the slider to whatever level you want. So now that I'm zoomed out, I can tell where we are, which is actually, as you can see in the optical view, we're basically looking at the very edge of that sample stub. So what I want to do is I want to move so that the center of my stub is in the center of view. Movement, again, several ways of doing it. The most common way is double-clicking the left mouse button, and wherever you double-click becomes the new center of the image. Another way of doing it is you click and hold the wheel on the mouse. It gives you a yellow dot and an arrow, and wherever the arrow points is the direction you go, and the farther the arrow is from the dot, the faster you move. This is really useful for scrolling around the large sample and trying to find the area that you want. Now, if you know the particular area, the particular spot that you want to look at, you can come over here to the second of the pull-down menus called Navigation, and you can put in an X and Y value. I want the center of the stub, so I'm going to go 0, 0 for X and Y, say go to, and there we go. So here we have my sample in view. I'm going to zoom in a bit. That my focal plane is not in the correct spot. I'm going to change the focus. Ways to change focus: manual user interface. The two knobs on the right hand side, coarse and fine. I can simply rotate them until I get a good focus. Another way of doing it is if I right click the mouse, it'll give me a double-headed arrow, and I can drag it left and right and change the focus that way. And last, up here along the GUI is an icon for auto contrast and brightness. If you click that, it will adjust the contrast and brightness. MUI knobs for contrast and brightness. There is also, under beam controls, sliders as well. Brightness and contrast really is crucial to getting a good image. Zoom in some more. So I did focus earlier, and it looked pretty good, but now that I zoom in further, I can see it actually wasn't that fine. So I'm going to touch it up a little bit further. And as I do so, you'll see that it's a little bit better, but my features are being stretched. As I try to focus in the opposite direction, now everything is stretched in this direction. This is classical astigmatism. Basically, it means my beam is not sufficiently round. You're not usually going to work at long distances, which is what we're at right now. We're simply going to get it as good as we can, where the astigmatism isn't pronounced. And then we are going to do what's called linking. It's a safety function. In the navigation window, under Z, it's got a red arrow. The reason for this is because the software doesn't know where your sample's at. All it knows is where the stage base is. We want to know where the sample is, because the last thing we want to do is to slam the sample into the pole piece. Working distance is the distance between the end of the pole piece and your sample. As long as you are properly focused, you know where your sample actually is. We're going to tell the software, this is where it's at, make that the new reference point. And the way you do that is with this icon right here. So I click on that. Here in Z, my arrow is now pointing down, showing that the reference point is the pole piece. It gives us a value roughly equivalent to what the working distance is. Now that we know where the sample is, we can safely raise it up to operating height, which on this particular instrument is approximately 5 millimeters. So I simply come over here, I highlight it. I just said the working distance is 5 millimeters. In reality, it will almost always overshoot. I'm going to put in about 5.2 and then click on the Go To button, because that then becomes a stop button. And then I can watch it in the optical view here, and if it looks like it's about to crash, I can press stop. No problem. I've got plenty of space left. If I look at my image now, you'll see it's back to being fuzzy. The reason is when I put in 5.2, the software automatically changed the working distance to match 5.2. But the stage didn't stop at 5.2. It went too far. So the focus plane is now different from where my sample is. So I'm going to have to refocus and get it as good as I possibly can. And then I'm going to click back over here to navigation, Z value. I'm going to put in 5, tell it to go. So now we are at proper operating height. But you can still see we still have significant stigmation issues. You can see it stretch that way. Now you can see it stretch that way. we're going to adjust the stigmators. There's several ways to adjust the stigmators. The most common one is the MUI knobs. Another way of adjusting the astigmatism is if you click Shift and use the right button on the mouse, you can adjust the stigmation that way. I usually will either use the MUI knobs or I'll come over here under Beam Controls. There's a subsection called Beam and Stigmeter. And so it's a white square with lines on it. If I grab one of the lines, I can adjust the stigmation on that axis alone. And pure and simple, basically what you're trying to do is you're trying to get as crisp an image as you can. If you have features in your sample with well-defined edges, that makes it much easier. The better your stigmation is, the sharper the edges are. So I don't really have anything like that on this sample. Instead, what I have are small features that are more or less round. So I'm simply going to try to make them as round as possible and as crisp as possible. So there we go. That's not too bad. So here I am. I'm at a much higher magnification. I'm going through focus, and you'll notice that I'm not getting stretching in either direction. This shows that my stigmation is well done. So we're now at the proper height. We've got preliminary focus and stigmation done. Let's go over some of the other controls along the top. So we've already talked about the magnification box here. Next to it is the high voltage for general imaging. If you're going to be doing especially surface work, 5 kV is the easiest to use. Next to it, this is your beam current. The larger your beam current, the larger the spot size hitting your sample, the more particles, which means the more signal you're going to be getting out of your sample, better your signal to noise, nicer, crisper images. The downside is because you have that larger spot size, your resolution is going to be poor. Generally, what you try for is some happy medium between the two. I could quite easily go down to, say, 98 picoamps and still get a perfectly good image. I like the higher signal to noise for the 1.6, so I'm going back to that. Let's say that I want to do some high resolution work. What that means is I need to align the beam system. So the first part of that is under Beam Controls, a subsection called Tuning. First thing we're going to do is go to what's called Source Tilt, and I'm going to click, there's a crossover button. So I click that, window turns black, and I get a green X, and you can barely see it, there's a bright spot. I want that bright spot to be centered on the green X. I have a box with lines in it, and I can simply just either grab individual lines, or if I grab the gray square in the center, I can have full freedom, and I just simply drag the white circle to where I want it. Once it looks good, turn off the crossover, and I know that my beam is now properly aligned with my gun aperture. If you do the crossover, and let's say that you can't see your bright spot, you can just simply increase your contrast until the bright spot appears. The next thing I want to do is I want to make sure that my beam is coming down straight. This is the lens alignment. Come down here to the beam section again, and there's a section called Beam Shift. All this does is basically use the lenses to basically push the beam. I'm going to right click, it gives me a menu, and I'm going to click 0. So now I know that my beam, it thinks, is coming down straight, but I'm going to test it. Doing the lens alignment is always easier if you have an easily recognizable feature, because what we're going to be doing is we're going to be looking for movement in the image. Come over here, and there's two ways to activate the lens alignment. One is under Beam Controls, Tuning, Lens Alignment. There is a modulator button. Other manufacturers often refer to this as a wobbler. Or you can come up here to the icon bar, and there is an icon right here, looks kind of like a target, called Lens Alignment. So you click that, and what you ideally want to see is the image going just in and out of focus. No movement at the center, or no lateral movement at the center. Here you can see There's not much, but there's a little bit of vertical movement. So I'm simply going to come over here to the lens alignment box, just like all the others. I can reduce it by axis or go for full freedom. Again, on this one, I tend to prefer to go by axis. And I'm going to try to get rid of that little bit of movement. So if you're way off, you can see you get a lot of movement. So got a little bit of left, right, left. Move too far. There we go. That's pretty much just going in and out of focus. So that shows that our alignment is good. So now we can zoom in even further. So we zoom in, we zoom in. Now, one of the things you'll find is that once you get beyond a certain point, your ability to improve the image seriously degrades. That is because you have reached the limit for this particular detector. So if we come up here to detectors, you can see check mark ETD parentheses SE. This stands for secondary electron. The other detectors that we have is the TLD. This stands for through the lens detector. TLD gives you a greater ability to go to higher magnifications than the ETD does. So you can simply go to the TLD. Now, you'll notice we've got a rather bright section here. When you see brightness in an SEM image, it usually means one of two things. Either A, your material is charging, which is not uncommon, especially if you have a non-conductive sample. Another thing it could be doing is you could actually be damaging your sample. So what I'm going to do now is I'm going to try to go find a feature that is more or less damage proof, like one of these. So 50,000, 65,000. Now, compared to the ETD, if you'll notice, even the smallest of these spots still jump out. They're well defined. But my ability to get signal off of them is poor. Right here, we have a little pull-down menu, and we have what's called mode 2, the immersion lens. Create a magnetic field around your sample, maximizing the number of electrons that can make it through the lens detector. One specific note on this, you cannot use the immersion lens with magnetic materials. So we go to the immersion lens, and it takes a few seconds. So we zoom out, we refocus. So we can see this details, but you can also see that the feature is changing. So now, I talked about astigmatism earlier. When you are trying to do high resolution work, you're going to find yourself going back and redoing your alignment and your stigmation. So I have my feature, and you can actually see here my sample is actually now being actively destroyed by my beam, creating a hole. This is actually just probably a piece of dust. So I go to my modulator. You can see again some vertical movement there. Because of the refresh rate that is going on, it is often very difficult to decide, is it better or worse? Up here along the icon bar next to the lens alignment, there's what's called the reduced area. Only the area inside the box is being scanned. This allows you to go to a higher dwell time without slowing down the whole imaging process. Definitely worse, better, worse, worse. We're at 200,000 magnification. If I do the full screen, we're now at almost 400. You can see these holes. Now, if I want to improve my signal to noise, I am going to collect an image. You're going to use the F2 button on the keyboard. This is going to give you a long dwell time image. And so now I can actually make out details that I could not before. High resolution work, stigmation, lens alignment, crucial to getting good imaging. The immersion lens is incompatible with the ion beam. We go back to quadrant system. So continuing along the icon bar here, we already talked about auto contrast and brightness. This is the auto focus that I mentioned earlier. It does an acceptable job. This is your dwell time. If you're doing long dwell time, you're spending a lot of time at that one point, you're going to charge it up more. Dwell time, if your sample is compatible with it, is a great way of improving your image. How do you increase your signal to noise if you go to a shorter dwell time? Is the next section. You can increase and decrease the number of pixels. The standard operating on this instrument is 1024 by 884. If you wish to improve your signal to noise, another way of doing that is what's called the filter mode. You have your choice of live scan, which is what we're doing right now. You have averaging and integration. And what this does is this takes, if you're doing, for instance, averaging, however many frames you tell it to. One thing that you will sometimes come across that related to the averaging integration issue, and you'll tell it to unpause, and it will immediately pause again. All this means is that the previous user had set this for a low frame rate integration. Just pull down the menu here, set it to averaging, and you're good to go. This camera represents the snapshot. Snapshot is a single moderate resolution, low dwell time image, single scan. The advantage of this is that you are minimizing the beam sample interaction time. Scan rotation is simply the angle at which the beam is rastering across the sample. So notice the angle of the box. If I change my scan rotation to 90, 180, and I can also type in particular angles. I can make it like 30 degrees. Navigation window, we already talked about being able to navigate in X and Y and Z. The system has tilt functions, so if you want to be able to look at the height of your sample, you can tilt. Here we have a sample that's got hole, so I'm going to tilt my sample to 45 degrees. My image is moving. I'm not truly at the best operating height. Easiest way to get around that is simply just reach over to the stage here, rotate the Z knob, and bring your feature back. I can now see the sidewall of my feature. So if I want to measure how deep this particular feature is, I can now actually see that back wall. I can skip over to processing, and there's this measurement and annotation section. I can do rectangles, circles, angles. In this case, what I'm interested in is a line measurement. Click at the top of it, drag it down to the bottom, and I have a measurement. Notice at the end of the measurement, there is a parentheses with an S on it. The reason for that is because this software has a tilt correction in it. Here under the line measurement control, you will actually see a line labeled tilt correction. It will automatically calculate what the tilt is based off of the stage. S means specimen. It's trying to measure a length across the surface of the sample. Whereas what we're doing is we're measuring into the sample. This is a cross-section view. So I'm simply going to come over here, click on cross-section, and you'll see that you always want to make sure that you've got the correct add-on here at the end of it. Rotation, self-explanatory, you're just rotating your sample. Compucentric rotation is very useful. Basically what that does is, let's say that you are out at the very edge of a large sample. If you simply do rotation, the area that you were looking at is now way off to the side. Whereas if you do compucentric rotation, it's going to calculate where that feature is. It's going to do the rotation and then move that feature back under the beam. You can save a large number of positions. So I can sit here and remove that, and I can say add a new one. And if I click on the name of it, I can rename it. So this is, I'm just going to call this one hole. And now if I go someplace else on the sample, add a new one. But if I want to go back to the first one, I can click on hole. And there we are. And then if you're done, don't need them anymore, you can just simply remove them. Detectors. In this video, everything we've done has been with secondary electrons. This system is theoretically capable of doing backscatter. It does not have a ring backscatter detector. The signal to noise is very poor. Last but not least, when you're done, you are going to put the system to sleep. What this does is allows the ion beam source to cool. It is a consumable, and then you're going to hit vent. As long as the GIS needle is not in, when you hit vent, it will automatically lower your sample and detilt the stage. If you had closed the gas cylinder, you're going to need to reopen it. Remember to close it when you're done. System is vented. See, the Omni probe is raised out. I can hear the gases escaping. Slide the door open, just like before. Loosen the set screw on the side. Pull out your sample. Close the door back up. And hit pump. Never leave the system in the vented state. It should always be pumped down.